In this video, I'm going to talk about the synthesis of Hunterine A, a natural product that features a 6,7,6,6,5 pentacyclic skeleton. The molecule can be isolated from the leaves of Hunteria Zeylanica, a plant that has been used in traditional Chinese medicine to treat skin irritations. Some of the key steps in the synthesis of this molecule involve the formation of the 7-member azepane motif through an azide-olefin cycloaddition. The quaternary center was prepared via an aza-Cope Mannich rearrangement from this bicyclic alcohol, which resulted from a diastereoselective 1,2 addition of the vinyl species to a ketone. Finally, the bicyclic ketone was obtained from a desymmetrization and a Beckmann rearrangement of a symmetrical bicyclic diketone. The synthesis begins with an unpollunt ylite addition of cyclopentanone to ethyl acrylate, activated with TMS triflate, giving the enone in 64% yield. The reaction is a beta conjugate addition of an enone to an activated olefin via the formation of an ylite intermediate, derived from a phosphonium salt of silyl enol ether. The ylite reacts with the activated olefin in the presence of trimethylsilyl triflate in THF at -78C to give the beta-alkylated enone upon elimination of the generated phosphonium salt with TBAF. For additional details on the reaction, check out this paper. The next step involves a 1,4 addition of a vinyl nucleophile to the beta-substituted enone. As expected, when vinyl magnesium bromide is used, only the 1,2 addition product is observed. However, when the Grignard reagent is added to all these reagents at -40C, the desired ketone is obtained in 75% yield. The addition of an organometallic reagent to an alpha-beta unsaturated carbonyl compound can occur either at the carbonyl function, producing the 1,2 adduct, or at the conjugate system, giving the 1,4 adduct. Reagents derived from unstabilized carbanions, such as organolithium or organomagnesium reagents, tend to act across the carbonyl group. In contrast, stabilized anions, such as organo-Cooper reagents, typically undergo Michael addition to give the 1,4 product. An intramolecular cross-Claisen condensation takes place with potassium terbutoxide to give the symmetrical diketone in 86% yield. The classic Claisen condensation involves the self-condensation of two molecules of a compound containing an enolizable ester. In the Dieckmann condensation, a molecule with two ester groups reacts intramolecularly, forming a cyclic beta ketoester. In this case, the enolate form of the ketone reacts intramolecularly with the ester group. The next step involves an asymmetric reduction to desymmetrize the diketone. Several attempts were unsuccessful, for example, the Corybak-Shishibata reaction. Ultimately, the desired ketoalcohol can be isolated in good yields using a modified Noyori transfer hydrogenation reaction employing this catalyst and a mixture of formic acid and triethylamine. The reaction gives the diol as the main byproduct, which can be recovered and oxidized back to the starting material. According to the seminal protocol of the Noyori asymmetric hydrogenation, this transformation allows the enantioselective reduction of the ketones with hydrogen and catalytic amounts of bina-ruthenium 2 complexes. For more details, check out the chemist's cookbook. The enantioenriched alcohol is first protected with TBS chloride to give the silyl ether. The ketone reacts then with hydroxylamine hydrochloride to give a mixture of two isomers that can be isolated by flash column chromatography. When the desired oxime is exposed to an excess of thionyl chloride, a rearrangement occurs to produce the desired lactam in 75% yield. This is the Beckmann rearrangement. The Beckmann rearrangement allows the conversion of an oxime to the corresponding amide under acidic conditions. The stereochemical outcome of this rearrangement is predictable. The R group, anti to the leaving group on the nitrogen, migrates. Treating the lactam with lithium aluminum hydride results in the formation of a secondary amine. These conditions also result in the cleavage of the silyl protecting group. The amino alcohol is then selectively alkylated with potassium carbonate and bromoacetonitrile to give the aminonitrile in 80% yield over 2 steps. Swern oxidation of the alcohol delivers the bicyclic ketone in 84% yield. The Swern oxidation allows the preparation of aldehydes and ketones from primary and secondary alcohols. The MSO reacts vigorously with oxalyl chloride when no solvent is present. It can lead to an explosion. The most common solvent for this transformation is DCM. The oxidation is usually conducted at -78 C to stabilize the intermediates of the reaction. The 1,2 addition of the vinyl iodide to the ketone is not straightforward. Ultimately, the reaction proceeds through the generation of a dianion by the protonation and magnesium halogen exchange, followed by subsequent addition to the ketone. Under these optimized conditions, phenyl magnesium bromide is used to deprotonate the NH of the vinyl iodide. Magnesium halogen exchange occurs using a turbo-Grignard reagent, generating the dianion that reacts with the ketone. In this particular case, the use of lanthanum chloride salt is critical for promoting the 1,2 addition. Finally, Bock protection is carried out with TMS chloride in methanol, giving the alcohol in 59% yield. The aniline is converted to the aryl azide in 73% yield under these conditions via formation of an aryl diazonium salt. When copper salts are employed, this transformation is known as the Sand-Meyer reaction. Exposing the substrate to silver nitrate in ethanol initiates a tandem aza-Cope rearrangement Mannich cyclization via a formaldiminium ion intermediate. Here, the cyanomethyl group serves both as a nitrogen protecting group and as a precursor to the formaldiminium ion that triggers the aza-Cope Mannich reaction. In this case, silver nitrate effectively traps cyanide, activating the cyanomethyl group. The aza-Cope Mannich reaction involves a 3,3 sigmatropic rearrangement of an unsaturated iminium cation, generating the iminium ion and an enol which participate in a subsequent intramolecular Mannich reaction. This transformation represents an interesting strategy for achieving ring expanding annulations. The 5-member ring expands to form a 6-member ring. For more details, check out this chapter on the topic. Dissolving the azide in heptane results in a spontaneous azide-alkene dipolar cycloaddition at room temperature to give the triazoline in 80% yield. The desired diastereomer is then irradiated with UV light to form an azididine intermediate that is quenched with acetic acid to effect a regioselective ring opening. This intermediate is deacylated using potassium carbonate to give Hunterine A in 54% yield. Thank you for watching. I hope you enjoyed the video. Please subscribe, like, or leave me a comment down below. I'll see you in the next video. Bye!